Okay. All right, so we are about to start. Please come forward and have a seat. So today we will continue our discussion on the property of difference equations. Systems that are characterized by difference equations, and they have the system function, the impulse response. The last two times perhaps, we've talked about how to please stop eating. Okay, please stop eating. No. 上课了啊。So we have talked about a linear time invariant system and its impulse response. The last time we actually spent 2 times perhaps to talk about how do we solve the impulse response given the difference equation. So there are 2 methods if you remember, and one is from D transform. The other one is through linear algebra, eigenvalue decomposition. Okay, so there are 2 different methods. So that's about how you calculate the impulse response. And this time, today is the only time we meet in this week. Okay, so this time I'd like to share with you how we are given a system function, and then we know that it has the bottom part, the top part, right? BZ divided by AZ. Okay? And B and A are polynomials. So each of them has roots, right? So we have poles and zeros. And so today I want to share with you how the magnitude and phase response, are influenced by the presence of one pole or one zero. Okay, let me say that again. So today we are going to talk about the influence to the magnitude and phase response due to the presence, due to the presence of a pole or a zero. Okay, and you'll see very soon that the effect due to the presence of a pole is exactly the opposite of the effect due to the presence of a zero, because one is on top, the other is at the bottom, okay, of that system function. So that's today's main topic. And then we'll talk about the influence by 1, 0 first. And then next, that's probably pretty fast. And then next we will talk about a special example that is called the all-path system, which has 1, 0, exactly 1, 0, and 1 pole at inverted locations. 反转的位置 inverted location. Now what does that mean? We'll touch that in a moment. So today's topic really is the influence to responses. Magnitude. We talk about both magnitude and the phase. By poles and zeros. We first talk about the first example will be an example of having only one pole. The 1, 0, I mean. And we will denote the system function as simply 1 minus this 1, 0 at location, this location. That's our first example. And the second example is an all-path system. Which has the system function of something like z minus 1 minus a complex number, the complex conjugate of the complex number. And at the bottom we have 1 minus a the inverse. Okay, that's called an all-path system. I will cover that in a moment, after we're done with item number 1. Okay? All right, so but before we jump into item number 1, let's review this idea of being able to factorize the system function. Okay, to factorize the system function. So still we have this general notion of hz being the ratio, the rational function of that consists of that is the ratio of two polynomials. On top we have dk, d to the minus k power. At the bottom we have ak, d to the k power. And in general, of course, we have, there must be some kind of upper limit depending on the order of the polynomial. 就像是几次都这样 the order of the polynomial. Okay? I'll just skip the details there. You can fill it in. So last few times we mentioned that this can be factorized if we first pull out the constant term, the leading coefficients, and then factorization tells us that we can change the summation into a product. And there we have 1 minus ck d inverse here, and at the bottom we have a multiplication over index k, 1 minus dk d inverse. Okay, so that's our that is still our notation. As to talk about magnitude and phase response, we know that we need to use this system function and evaluate it on the unit circle, because that gives us the DTFT. Okay. So here you assume. So before that, let me make some assumption here. So here we are interested in, because we've shown an example that a system like Fibonacci series, that kind of system are unstable. Okay, so we're not interested. I've shown you that when you talk about this transform, you need to always consider whether or not its region of convergence includes the unit circle. Because, in other words, so here's the remark. So here we assume the system is causal stable. Both causal and stable. So in other words, if we make this assumption, then we are requiring that. In other words, we are requiring that all the poles are located. In other words, we are requiring all the poles are located inside the unit circle. Okay, some people might have learned it, but some might not. But this is an important concept. Okay, so we want all the poles to be located inside the unit circle, inside that circle of radius 1. Because that would guarantee that when you solve the impulse response, you know that impulse response consists of a sum of geometric series, right? And each geometric series has a common ratio. And what are those common ratios? Those are exactly the location of the poles, right? So if any one of the common ratio, any one of the poles is located outside the unit circle, that means that its absolute value is greater than 1, right? So if any of that common ratio, those common ratios has an absolute value that's greater than 1, the impulse response is going to explode. The impulse response will not converge to 0 when time approaches infinity. So that's why if we are only interested in systems that are causal and stable most of the time, because you're going to design a system later, right? And you don't want to design a system that is unstable, okay? Then that will be playful, okay? That will not. Most of the time, we don't design systems that are non-stable unless you design an oscillator or a non-linear system, okay? But that's outside of the scope of this semester. So let's assume that for now. In other words, let's assume that all the poles are located inside the unit circle. Okay, they might go from 1 to, I forgot, order n, okay? So there might be up to so many poles, but all of them are located, we're requiring all of them to be located inside the unit circle, not including the boundaries, okay? Inside the unit circle, no equal sign here, okay? Equality is not allowed. Any questions so far? Right? Okay, so with that being said, so now if all the poles are located inside the unit circle, we know the region of convergence. The region of convergence will include the unit circle. Okay? The notation of the region of convergence is a set, a subset of the complex plane. Okay? Which includes this set. This is a notation that is all the points on the unit circle. So if all the poles are located inside the unit circle, then the region of convergence will include the unit circle. So we can evaluate. So we can evaluate h of z on the unit circle. In other words, DTFT can be calculated. It's this. Okay, so that's the kind of underlying criterion. Every time when we talk about magnitude or phase response, we need to assume that DTFT has to exist. What is a sufficient criterion for sufficient condition? A sufficient condition for DTFT to exist is to require that all the poles are located inside the unit circle. Then we have a causal and stable system. Causal and stable system. Mainly, our concern is stability. The main concern here is stability. Okay, so if this can be assumed, then let's evaluate. Then this is DTFT of the impulse response. Let's evaluate the frequency response on the unit circle. Okay, we will evaluate the system function on the unit circle, and that can be done. Okay, just replace z by e to the omega everywhere there. Well, I want to show you that here. Let's try to consider magnitude and phase separately. Okay, let's first take a look at the magnitude response. So the magnitude response really is this DTFT taken the absolute value. And here, let us consider the magnitude response in log scale, in dB. Okay, let's try to consider that in log scale, right? Okay, so in log scale, in dB, taking 20 log 10. Now we know when you take the log of something, multiplication becomes summation, right? So here's the deal. So then we have, and here is the absolute value. Okay. So we will have this first constant term here, which is a constant. This is a constant, and then we have summation. Okay, so this time let me just clearly write down n and n. So this must be n. So we have the contribution from every single zero and every single pole in this following way. So 1 minus c e to the minus j omega. That's the contribution of, this is the contribution of every zero its contribution to the magnitude response. Okay, this term, this individual term. Now, after taking 20 log 10, taking 20 log 10, this term is exactly the contribution, the contribution of to the magnitude response due to the presence of 1, 0, every 0, C1, C2 to C10. Okay, and similarly, we have the contributions from poles after taking 20 log 10. So this term is a contribution. This term describes the contribution to the magnitude response due to the presence of every pole. So every one of them here is a 0. And every one of them here is a pole. And they all have their contribution. They all contribute to the magnitude response. And it's clearer when after we're taking 20 log 10 absolute value. Okay? Are we good here? Are we good here? So that's why, so this is one of the reasons why we like to take 20 log 10. Because the contribution to the magnitude response now is added on top of one another. Okay? This becomes an addition. So then it's easier for us to separately consider the special case. What if we just had 1, 0, the simplest case? The simplest case will be a system that has only 1, 0, no poles. Okay? So that's why it's now our focus. Now our focus is to look at 20 log 10, 1 minus ck e to the minus j omega, after taking the absolute value here. Let's just focus, because this is constant, this is not interesting. Okay? This is just a kind of a DC overall scaling factor. Okay, that's not very interesting. But now let's just separately consider this term. How does it look like if we make a plot, if we make a sketch? Okay, so now let's focus on. So that's why I said our first special case, case number 1, will be the special case of only 1, 0. Because if we understand this magnitude response, then we understand pretty much everything here. Okay, so next we're going to see what properties we can figure out. Not only the magnitude response, but also the phase response. So let's focus on the magnitude response. I'm gonna give it a name. Okay, so this magnitude response will be after taking 20 log 10. Let's denote it as a big M of omega. M stands for magnitude. Okay? Let's define M of omega as 20 log 10. Actually, okay, 20 log 10. 1 minus ck e to the minus j omega. And where ck might be located anywhere on the complex plane. Okay, anywhere on complex plane. Note that here we don't generally we don't need to require 0 to be located inside the unit circle. 0 can be anywhere, okay, pretty much anywhere. And so here, so let's assume that there's 1, 0 somewhere on the complex plane. And so to draw kind of a, let's just show it on this complex plane with real part and imaginary part. And let's assume that, for the sake of discussion, let's assume that our 0 is located right here, okay, with a angle theta, if you will, and the radius of r. Radius of r and angle of theta. In other words, let's assume that ck is r e j theta. All right? Let's assume that for the convenience of discussion, let's assume that the radius is located at radius r and angle theta, with an angle at the angle theta. Okay, then let's keep on here. So if you really work it, so now after defining the radius and the angle, then y minus, so let's replace this location of the 0 by its polar notation. Polar representation r e to the j theta e to the minus j omega. Okay, that's just a simple substitution. All right, so if I ask you to make a sketch, make a sketch of m of omega. Let's try to make a sketch of m of omega. So how do we proceed? Let me show you the result first. The result, if you will, this is a system that has only one zero. Okay, so it turns out that near theta will have a minimum. The magnitude response will reach a minimum. It reaches a minimum exactly, and we'll show that. It reaches a minimum at exactly the frequency theta. Now theta is actually a frequency. I said angle, but angle around the unit circle is a frequency. Okay, so at frequency theta, it reaches, the magnitude response reaches a minimum. Now, whereas if we consider from 0 to 2 pi, okay, 0 to 2 pi, whereas at theta plus pi, maybe somewhere here, at theta plus pi, that's also a frequency. At this frequency, we'll show that the magnitude response reaches a maximum. A maximum. Okay? So that's fairly simple. Maximum somewhere, minimum somewhere. And we may just kind of draw a sketch, right? So that's the magnitude response. With a minimum, it turned out that the minimum is something, and if I remember correctly, the minimum is 1 minus r, the maximum is 1 plus r. Now, why is that the case? The question is, this is, I'm just jumping ahead. This is the result. Okay, this is the kind of sketch. The magnitude response due to the presence of a zero located at frequency theta with radius r. But why is that the case? So let's continue our continue working on m omega. Okay. So one way is to show that this is not actually that hard. Oh, I'm sorry. This is 20 log. We have 20 log 10. Right. 20 log 10. So let's continue working on m of omega a little bit. So we'll see that actually this expression here, if you work it out, you can show that it's equal to 1 plus r squared minus 2r cosine theta. You can work it out. Okay, you can certainly work it out. Wait, not cosine theta, omega is done. Omega minus theta. Sorry about that. Okay, so that's the expression. You can work it out. Any question here? Yeah? So that's an expression. So it's actually not that hard to derive the closed form expression for the magnitude response to dp. Okay? It's not that hard. And so just by inspection, if I ask at what frequency does this expression reach a minimum and maximum? We ask that question. Okay? So this is 1 plus r squared plus something 2r cosine. And cosine is in between minus 1 and 1, right? So when does this function reach a minimum? A minimum is for this term to be maximally negative, right? So when is it maximally negative? That's when cosine of that is equal to 1, right? So that's why you can hopefully add, you can say at omega equal to theta, cosine omega minus theta reaches maximum and n of omega reaches minimum, which is 20 log 10, and 1 plus r squared minus 2r taking the square root. So I'm pretty sure you can see that y it is just 1 minus r. Okay? Here, of course, on the plot, I'm assuming that r is less than 1, smaller than 1. Okay? So otherwise, there might be a. Now let me just be clear. There could be an absolute value around 4 minus r. Is minimum. So we've shown that this minimum really occurs at frequency theta. Okay? So this is kind of a useful piece of concept. A useful concept, right? So I don't really want to deliver this. This is a useful concept. Whenever we have a 1, 0 somewhere on the complex plane, then you want to consider its angle. Okay? Two things. One is the radius, the other is the angle. Okay? So first of all, we can expect, due to the presence of using this derivation, due to the presence of this this 0, it kind of pulls down the magnitude response near its frequency, near that angle. The magnitude response reaches a minimum, which means the gain is the smallest, the lowest. Okay? So if you just deliver an input to this system, the output is smallest at exactly this frequency, due to the presence of that 0. Right? And so that's about the angle. But how deep is the dip? What's the depth of this dip? Any idea? The depth of this dip, very simply, depends on how close the 0 is located near the unit circle. How close is r to 1? The closer r is to 1, the closer the 0 is located near the unit circle, the deeper this dip is. Let me say that again. The closer we push the 0 toward the unit circle, let's say if we put it really, really close to the unit circle, very close to the unit circle, then we expect 1 minus r to be close to 0, right? Close to 0. So taking log 10, it can just reach minus infinity. Okay? And that makes a lot of sense, because in the extreme case where the 0 really touches, is located right on the unit circle, that means the gain over there, when the frequency reaches there, the gain over there is exactly 0. And what is 20 log 0? 20 log 10 0 is minus infinity, which means that the signal at that frequency will be totally cancelled out in the output. Okay? So, but anyway, of course, by increasing r toward 1, the maximum gain somewhere, the maximum gain there can approach 20 log 10 2. Not very interesting. But what's more interesting that by presenting a 0 somewhere at a frequency, then we can pull down, we can reduce the gain at that frequency. So this is a very useful concept. Let's say now you're implementing a system, okay? You might be given the sampling rate. The sampling rate is 16 kilohertz. And you want to implement a system so that its gain at 4 kilohertz reaches the minimum. How do you do that? Simply, the simplest thing you can do is to try to put a 0 around the frequency of as the sampling rate is 16 kilohertz, right? If you want to put a 0 near frequency 4 kilo, that means where do we put the 0? The 0 should be located at e to the j 90 degrees, because 2 pi is 16 hertz, 16 kilohertz. So 2 pi divided by 4 is 4 kilohertz. That's okay. So let me just summarize what I just said. Example is sampling rate is 16 kilohertz, and you want minimum gain. We want the system to have a smallest gain at exactly frequency 4 kilohertz. Okay? And I was just saying that, I was just suggesting that 16 is equivalent to 2 pi, to omega of 2 pi. And 4 kilohertz, therefore, is equivalent to pi over 2. Therefore, the result, you can just simply, and this is already a design, okay? This is our unit circle, and you can just place at this angle, 90, which is 90 degree, pi over 2. Real part, imaginary part. Just place the 0 somewhere on the y-axis at angle pi over 2. Then that will do the job. And you can consider where exactly you want to put the 0. Is it really close to the unit circle, or is it kind of still at a healthy distance from the unit circle? You can decide. Okay? Because you know that the result of your design, you have a minimum gain, exactly 20 log 10 1 minus r. Any question? Okay. So if no question, then let me keep asking. Let me ask you a question. Can you write down, okay, so now we place a 0 right there. What is the corresponding difference equation? Because we need to implement the system, right? What is the corresponding difference equation? And can anyone tell me? Okay, can you discuss with your neighbors for 1 minute? What is the corresponding difference equation? Y of n, how does that relate to y output in pad and input up to the present time? Okay? That's the difference equation. So how do you write down the difference equation that does the job? Anybody? Any suggestion? You don't need to work out all the details. Any suggestion? Any suggestion? What is the corresponding difference equation? 张道宇说。2分之3代入 omega. To substitute pi over 2 into omega. Yes, and then do the inverse transform. Right. Yeah, you can do that. Yeah. Theoretically, that's nothing wrong about that. Okay. Any easier way? I just need the answer. Okay. What is the corresponding difference equation? What's the corresponding difference equation? This is actually not that hard. Okay, but thank you for your suggestion. Okay. The corresponding difference equation. Let's just keep working on this. So now we have so let's say we are suggesting you to put a 0 at r e to the j pi divided by 2. Okay? What is e to the no, it's plus. Okay, no. We're suggesting you to put a 0 somewhere there. So what is some detail here? What is e to the j pi divided by 2? J, right? Okay, so we are suggesting you to put a 0 at this place. Therefore, we say the corresponding system function will be 1 minus JR Z inverse. Right? We're putting a 0 exactly right here. R could be a parameter that you can adjust. So far, so good? So what is the corresponding difference equation? The corresponding difference equation becomes y of n equals to x of n minus JR x of n minus 1. That's the answer I want you to come up with. Okay? So that's actually pretty easy. Pretty easy, right? But there is a problem, some kind of a desired property in this difference equation. Do you notice? You notice something undesired. 不爽,不理想. What's that point? The point of a property that is kind of undesirable in this difference equation. Now we have a complex coefficient, a purely imaginary coefficient, and usually you don't want to do this, okay? You can do this, of course, if you have data structure, you can use using Python, but let's say you're implementing your system in fixed point computation using C++. Okay, it's not so desirable to have when we go back to the time domain, we want everything to be real. So remember, in the beginning of this semester, I mentioned that most of the time we assume our signals are real unless otherwise mentioned. Okay, so let's say your input is real. But now here the output is complex, and that might not be desirable. I mean, this is something that you might want to avoid. Okay, so so how do we fix this problem? If we say, okay, yeah, great, your system has a 0 near frequency pi divided by 2, but you're giving me a difference equation that contains complex value coefficients. Can you modify it? Can you keep everything real? Can we keep everything real, but still having a minimum magnitude response near frequency pi divided by 2? Then how do you fix this problem? Okay? Any suggestion? 来，你说看，戴雅欣嘛，对吧？你戴雅欣，你是戴雅欣吗？对啊。你说看。Okay, so now we have this problem of a complex value coefficient. Here, 复数的. I said that's undesirable. Okay. So how can you change the system design to still satisfy this specification, but keeping everything real? 这边怎么改？这边才会要让这边还是 real。 Yes. Okay, so you mean so one suggestion here, add a pole here. So now let's say the pole is alpha. So could that work? No, yeah. Okay. Any other suggestion? Well, thank you for considering. Okay. 苏华你说看啊。后面这位女同学啊，穿红衣服的。How do we modify the system so that we want to keep everything real, but still having a minimum response at this exact frequency? How do we do this? How do we do it approximately? Okay. 这位女同学，你说看。Exactly. Okay. So she said that's the kind of one answer I was looking for. Okay. So her suggestion is that okay, so we want to keep everything in real. Then the problem really is that when we have a 0 somewhere, a single 0 on the unique on the complex plane. The problem, so you see that having one single 0 arbitrarily on the complex plane will cause the coefficient to become complex value. Okay, so a simple fix for that is wherever we have a 0 somewhere, put a 0 at a conjugate location. Put the 0 at the conjugate location, same r minus theta. Okay? Put the 0 somewhere. Then now our system function becomes h of z. After putting in that one extra 0, then our system function becomes 1 minus c Z inverse times 1 minus its complex conjugate Z inverse. Right, so now strictly speaking, we have two zeros. Of course, it's not a single zero system anymore. But we know that fair enough that the magnitude, their influence to the magnitude response would be a sum. Their influence is sum in log scale. So that's pretty simple enough. But now, after introducing this extra zero, then what we have here is something like everything will become real. Okay? Because this is exactly 1 minus, let me work it out, 2 times real part, ck, z inverse. And now, the z to the minus 2 term, the square term is exactly ck squared, z to the minus 2, to the minus 2. Okay? So now you see that everything here, all the coefficients become real valued. Therefore, we can write down the difference equation. We can implement this system by defining yn to be x of n minus 2 times real part of this complex number, x of n minus 1 plus the square of absolute value, x to the second sample in the past, second samples ago. Okay. Any question here? So thank you for the suggestion. Okay. So this is the kind of in reality when we need to keep everything real. So wherever we desire to put a zero somewhere on the complex plane, if it happens to be complex values, you should consider putting another zero at the conjugate location. Okay? All right, thank you all for considering this question. And so that's the special case of having the influence to the magnitude response due to the presence of 1 0. Okay? So if we know the influence of 1 0, then we know also in very straightforward manner. Very similarly, we can know the influence of one pole when we have only when we have one pole somewhere on the new circle. The influence is exactly the opposite. Okay? So I'll not just go through repeat the derivation. So let me just draw a sketch. When we have one pole, somewhere, usually we would put a cross, like the we put an X to represent the location of the pole. Okay? When we have one pole somewhere at theta, then we expect to see a peak. We expect to see a peak, a maximum near that frequency theta. Okay, so the plot will be exactly upside down. Exactly upside down. We expect to see a peak. We expect to see a peak at the angle, which is the frequency. Okay, at exactly that frequency theta. And that's it. Okay, that's the influence of the contribution of the pole to the magnitude response after taking 50 log n. Okay, so we can say this is in dB. Okay, so this is the contribution of the pole to the magnitude response. Okay, so let's take an early break here, and CA, could you please return the back?